Okay, so I kind of ended the last video a little abruptly just because I felt like it was getting a little bit long, but we basically just showed that we have two different ways of representing complex numbers. We can represent them here in rectangular form, which we saw is just based on the position of the point that we're interested in the complex plane on the real and on the imaginary axes, right? And we also can represent them in phasor form or polar form by representing them first by the length of the vector or line drawn from the origin to our point in the complex plane. That's this r value here. And then secondly, by the angle that that line makes with the positive x-axis, where in this case it was 33.7 degrees, right? And of course, I use the exact same equations I used previously to convert from rectangular to polar, and I can use the exact same equations I used to convert back from polar to rectangular. If you remember correctly, that was, so if I wanted to get my x and my y values here, or in this case, my real and my imaginary components back from this complex number, I could just say that x is equal to r times the cosine of the angle, which would be 7.2 times the cosine of 33.7, and I would get a value of 6, and I could say that y is equal to 7.2 times the sine of that angle, and I would just get 4. Okay, so the same equations apply, which is nice. This is where it all comes together. Everything we've talked about, the sine waves, why did I cover vectors? Why did I cover rectangular and polar? Why did I cover phasors? The reason I did all this is because these phasors can actually be used to represent our sinusoids. Again, our sinusoid comes from a vector just like this one, spinning around in a circle, right? That's all our sine wave describes. It describes the motion of this vector along a circular path, and if we give it some frequency, it's just going to keep on going around and around, and it just becomes, we track the y coordinate, and that gives us a sine wave. We talked about all this. Well, what I said previously is that when we look at circuits with a sinusoidal input, so for example, I drew a circuit like this, where I had a resistor here and a resistor here. When I look at circuits with linear elements like resistors and inductors and capacitors, the only two things that change from one node to the other, if I'm finding voltages or I'm finding currents, the frequency does not change. Nothing about my circuit will change the frequency of the signals. The only things that will change will be the amplitude of the sine wave. So again, I'll write it as Vm sine of omega t. Oops. Plus some phase. The only things that will change will be my amplitude and my phase, okay? So what I can do is, let's say I've got a sine wave that's something like, let's go on to the next slide. I've got a little blank slide here. I can use this to draw. So let's say I've got a sinusoidal source here, and let's say that this Vs of t is equal to 5 times the sine of omega t minus 15 degrees. Okay, that's my Vs of t in volts, and I can represent this by just its magnitude and its phase, right? If I were to take the amplitude of 5 or whatever and the angle of minus 15 degrees, I would get something that looks like this. I would be at some point where the length of this vector is 5 and the angle from the positive real axis is negative 15 degrees. And now I can just sweep this thing around in a circle, and that would be my sine wave, just starting at this point at time t equals 0, right? But nonetheless, I can represent this sine wave and all that I have here just from its magnitude and its phase. So I could rewrite Vs of t as 5 angle negative 15 degrees volts. I can just completely drop the sine part, and I can completely drop the omega t part, because like I said, if I'm solving circuits, other points in my circuit are not going to change anything other than the amplitude and the phase. So I can actually go ahead and just represent the entirety of my sine wave just like this. I don't need to represent it in terms of the full time domain signal. I can just use phasors. This box is just not working out for me, so let me just draw this ugly box. It's not going to be as nice. But why would I want to use phasors? Why would I even want to do that? What would be the benefit? Well, the benefit is that when we go through to do all this math for these circuits, we're going to need to do a couple of different things. We're going to need to add, we're going to need to subtract, we're going to need to multiply, and we're going to need to divide. And when it comes to adding two sine waves, I highly doubt that you want to sit here and take something like 5 times the sine of omega t minus 15 degrees and add it to something like 3 times the cosine of omega t plus 72 degrees. Taking those and adding them would involve trig identities and trying to look up your trig identities and figure out which one you can use and making sure you have your angles right and converting both of them to sine by shifting this angle, yada, 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 yada. That's not fun at all. So instead, what you can do is once you get the omega t's, completely to be neglected because we know that they're the same frequency, we can just sit here and convert both of these to phasors. So in this case, I shouldn't have used a cosine here just because now I have to take into account the 90-degree phase shift that's associated with a cosine. So let's just write it as a sine. I could write this guy as 5 angle negative 15, and I could write this one as 3 angle 72. And not that this is particularly easy, but from here I can go a step further. I can even go right into the complex domain where I have the rectangular values, where x is equal to 5 cosine of minus 15, y is equal to 5 sine of minus 15, and the same here, x is equal to 3 cosine of 72, and y is equal to 3 sine of 72. And once I do this, I'm basically going to have x plus jy for the first value. We'll just call this x1 plus jy1, and I'm going to have x2 plus jy2. And to add those, all I need to do is x1 plus x2 plus jy1 plus y2, and I would be done. I would have just added these two sine waves together. So I can just bounce between phasor form and rectangular form and very quickly do the kinds of math that I need to do in order to solve my circuits. Instead of having to use trig identities and all this ugly math in the time domain, I can go right into the complex domain and make the math much, much easier for myself. So that is why we're doing all this. That's the reason for phasors. And so I have y phasors here. Well, let's just say that I keep rectangular on this side and phasors on this side. If I'm doing addition or subtraction, it's much, much easier to take x1 plus jy1 plus x2 plus jy2 and add those, because like I said, it's just going to be x1 plus x2 plus jy1 plus y2. Phasors are not super easy to add in phasor form, but they are super easy to add in rectangular form. Same with subtraction. x1 plus jy1 minus x2 plus jy2 is just equal to x1 minus x2 plus jy1 minus y2, okay? Now, in terms of multiplication and division, I'll actually just go ahead and stop this video right here because I think this has gotten quite a bit long, but in the next video, I'm going to show why in phasor form, multiplication and division are even easier than this addition and subtraction in the rectangular form. But again, the point of this video is just to show you that we can represent sinusoids as phasors, and by doing so, we allow ourselves to bounce between phasor form and rectangular form to make the math for these circuits much, much easier on ourselves than it would be if we left everything in the time domain, okay? So maybe that's not enough motivation for you, but I promise you once we get into solving the circuits, you're going to see why this is so powerful. Okay, so I'm going to go ahead and stop this video here.